Hello and welcome to LuckyMath. I'm looking forward to introduce you not to just any exponential function, but to the exponential function. So the exponential functions are the following, namely f of x is equal to a to the power x, where the base a can be any real value which is greater than 0 and not equal to 1, and the argument x can be any real value. So this could, for example, be 2 to the power x or 3 to the power x. And somewhere in all these exponential functions also hides the exponential function. And we're going to construct it in this video. But first let me graph these two functions. So if this were to be f of x, then this has to be the x-axis. And the function 3 to the power x would look approximately like this. Whereas the function 2 to the power x would look approximately like that. And you can see that both functions cross the y-axis at the value 1. And this is a universal condition for all exponential functions, because if you set the value 0 as an exponent, then a to the power 0 will just equal 1. So all exponential functions cross the y-axis at the value 1. Now for the beginning, let's just call this very special function that we're looking for g of x. And g of x should satisfy two conditions. And the first condition is that it really is an exponential function, which means that this function as well should cross the y-axis at the value 1. Therefore, g of 0 has to equal 1. And it is the second condition which makes this function so very special. Namely, its derivative with respect to x should equal the original function g of x. Now let's just assume that g of x was equal to the value 1. Why 1? Because then it would already satisfy the first condition. G of 0 equals 1. Okay? Now let's calculate the derivative. G prime of x would be 0, right? But we have a problem because we should satisfy the second condition, which says that both of these functions should be equal. Now let's just try and set this value equal to 1 as well. And now the second condition would be satisfied. But this would not be the derivative of this function. So let's adjust g of x such that this really is the derivative of g of x. And what we do is we add x because the derivative of x is equal to 1. But now the second condition says that these functions again should be equal. And now let's adjust g of x again such that this really is the derivative of g of x. And let's add x squared divided by 2, because the derivative of that will equal x. And now second condition says we have to add this here as well. And now again let's adjust g of x. And we get x cubed divided by 6. And the second condition says that we get the same term here as well. And we can do this until infinity if you'd like, but I suppose you don't want that. And therefore let's look for some pattern in here. And you can see that 6 is just equal to 3 factorial. Why? Because 3 times 2 times 1 is just equal to 6. And 2 is the same as 2 factorials. And if we divide x by 1 factorial, this won't change. And if we divide 1 by 0 factorials, this won't change either, because this is the same as 1. 0 factorial is defined as 1. And now we can rewrite this g of x as an infinite series, as you can see now, and I'm going to write it in red because this is a very important series. So what we get is the sum from n equals 0 until infinity of x to the nth power divided by n factorials. And this right here, this is the exponential function. This is what defines e to the power x. So if you set your argument in e to the power x, or in this series, you will get the same result. And we will get the same infinite series for the derivative. So this as well would be the sum from n equals 0 until infinity of x to the power n divided by n factorials. And this as well is e to the power x. And you can see that this function really satisfies both of these conditions. Because if you set the value 0 into g or into this infinite series, what will be left is only 1 because all of these x's will be 0. And the second condition is satisfied as well, obviously, because now the derivative is just equal to the original function. And now I'm sure that you would be interested in what is actually this value e. And we can use a simple trick, which is to set x equal to 1. Then we would get e to the power 1, which is just the same as e, right? And now we can set 1 also as an argument in this infinite series. And what we will get is the sum from n equals 0 until infinity of 1 to the nth power. And this will just equal 1 because 1 to any power will give you 1 back. And this divided by n factorials. And if you write out some terms of this series, you will get 1 plus 1 plus 1/2, and so on, infinitely many terms. And this would be approximately this number right here, 2.718, and so on. And this is the Euler number E. And this is a very special number because it is an irrational number, which means that you can't find a pattern in the decimals of this number. So whenever you write E, actually this constant here hides behind it. Okay, and what makes this function really so very special is that the derivative of the function with respect to x is just equal to the original function e to the power x. And this is the only function which satisfies this condition. That's why I always say the exponential function. And the last step I would like to take is to graph this function up here, and you will find that it is approximately this function. This would be e to the power x, and it is and because e is just 2.718 and so on to the power x, and therefore it has to be somewhere in between these functions. Thanks for watching, rate the video, subscribe, and see you soon again on Lucky Math.